We live in extraordinary times. A technological revolution is reshaping our world at an unprecedented pace. This revolution is driven by artificial intelligence, or AI, and its powerful subset, machine learning. From personalized recommendations on Netflix to self-driving cars, AI is influencing our lives in countless ways. In healthcare, AI diagnoses diseases with greater accuracy and personalizes patient care. In finance, it detects fraud and optimizes investments. As AI advances, it will fundamentally change the way we live, work, and interact with the world. If you are new to our channel, like, comment, share, and subscribe. Use the promo code in the description section to enroll in our AI and machine learning masterclass at a 50% discount. Machine learning empowers computers to learn from data without explicit programming. Instead of defining a cat's features, you show the computer thousands of images, letting it learn patterns on its own. This ability to learn from data makes machine learning powerful. In marketing, it predicts which customers are likely to make a purchase. In healthcare, it identifies patients at risk of diseases, enabling early intervention. Machine learning leverages data to solve real-world problems and improve our lives. The rise of AI and machine learning has created a demand for skilled professionals. Businesses are hiring data scientists, machine learning engineers, and AI specialists. This demand translates into lucrative salaries and exciting career opportunities. Beyond financial rewards, a career in AI offers the chance to work on cutting-edge projects and solve challenging problems. Whether you're a seasoned professional or a student, now is the perfect time to explore AI and machine learning. The skills you acquire will future-proof your career and equip you to shape the future. Let's delve into the fundamental concepts of machine learning. Machine learning teaches computers to learn from data, making predictions or decisions without explicit programming. Instead of rigid rules, algorithms learn from data, identifying patterns and relationships. This data-driven approach sets machine learning apart from traditional programming. Machines learn in distinct ways, each suited to different types of problems and data sets. Understanding these learning styles helps us grasp the power of machine learning. Supervised learning is the most common type of machine learning. The algorithm learns from labeled data, where each input is paired with its corresponding output. For example, predicting house prices based on features like size and location. The algorithm learns relationships between input features and the target variable. Supervised learning is divided into classification and regression tasks. Classification predicts categorical outputs, while regression predicts continuous outputs. Unsupervised learning deals with unlabeled data, uncovering hidden patterns. Clustering groups similar data points based on shared characteristics. For example, a music streaming service groups songs with similar attributes into playlists. Dimensionality reduction simplifies complex data sets by reducing variables while preserving important information. Unsupervised learning is open-ended and exploratory, revealing underlying structures. It's a powerful tool for tasks like anomaly detection and recommendation systems. Classification algorithms categorize data into distinct classes. They filter spam emails and personalize product recommendations. These algorithms learn from labeled data, building models to predict the class of new data points. Popular classification algorithms include k-nearest neighbors and support vector machines. Each algorithm has a unique approach to solving classification problems. Let's explore the concepts that make these algorithms tick. K-nearest neighbors, KNN, classifies data points based on their nearest neighbors. It looks for the k-nearest neighbors in a multidimensional feature space. The class that appears most frequently among these neighbors becomes the predicted class. KNN is simple and easy to implement but can be computationally expensive for large data sets. It memorizes training data and performs calculations only when classifying new data points. Despite its simplicity, KNN is effective for many classification tasks. Support vector machines (SVM) find the optimal hyperplane to separate data points. The hyperplane maximizes the margin between different classes. Support vectors are the data points closest to the hyperplane. SVM handles non-linearly separable data using kernel functions. It transforms the feature space into a higher dimensional space for linear separation. SVM is robust and generalizes well to unseen data, especially with high-dimensional datasets. Decision trees classify data points by asking a series of questions about their features. Each internal node represents a test, each branch an outcome, and each leaf node a class label. The tree is constructed by splitting data into subsets based on informative features. Decision trees are interpretable, making it easy to understand predictions. However, they can overfit complex data sets. Techniques like pruning and ensemble methods, such as random forests, help mitigate overfitting. Regression algorithms predict continuous outcomes, providing valuable insights. They handle problems like estimating house prices or forecasting stock market trends. Regression algorithms learn from labeled data, capturing relationships between inputs and targets. They predict numerical values, unlike classification algorithms that predict categorical outcomes. Regression algorithms are crucial for data-driven decision-making across industries. They optimize pricing strategies, manage inventory, and allocate resources efficiently. Imagine you're plotting data points on a graph, each representing the relationship between two variables. You notice a general trend. As the number of hours studied increases, the exam score tends to go up. Linear regression captures this relationship by finding the line of best fit. This line is represented by y equals mx plus c. Y is the predicted value, exam score, x is the input variable, hours studied, m is the slope, and c is the y-intercept. The goal is to minimize the sum of squared errors between predicted and actual values. Despite its name, logistic regression is a powerful classification algorithm. It predicts the probability of a data point belonging to a specific class. For example, predicting if a customer will click on an online ad. Logistic regression models the probability of a click event. Unlike linear regression, it outputs a probability score between 0 and 1. This score represents the likelihood of a data point belonging to the positive class. It uses a sigmoid function to squash the output within the probability range. A threshold value, typically 0.5, classifies the data point. Above the threshold, it's classified as positive, otherwise negative. Logistic regression is used in spam detection, credit risk assessment, and medical diagnosis. It helps make informed decisions by predicting event probabilities. Imagine you're trying to fit a line through a set of data points, but instead of aiming for the line of best fit, you're allowed to create a margin of error around the line, within which any data point is considered acceptable. Support vector regression, or SVR, takes this concept to heart, building on the principles of support vector machines to create a regression model that tolerates errors within a defined margin. Unlike linear regression, which penalizes all errors equally, SVR only penalizes errors that fall outside the defined margin, effectively ignoring errors within the margin. This margin of tolerance, controlled by a hyperparameter called epsilon, allows SVR to handle noisy datasets and outliers more effectively, preventing them from unduly influencing the regression line. Similar to SVM, SVR can also handle nonlinear relationships between variables by using kernel functions, which transform the original feature space into a higher dimensional space, where the data becomes linearly separable. This allows SVR to model complex relationships that might not be captured by linear regression. SVR is a powerful regression algorithm that offers a good balance between accuracy and robustness. Its ability to handle nonlinear relationships, tolerate errors within a margin, and resist overfitting makes it a suitable choice for various regression problems, especially when dealing with complex data sets or when the cost of large errors is a concern. In the ever-evolving landscape of artificial intelligence, neural networks stand as a testament to the remarkable ingenuity of human inspiration. Modeled after the intricate workings of the human brain, these computational marvels have emerged as the driving force behind some of the most transformative advancements in AI, pushing the boundaries of what machines can achieve. Imagine a network of interconnected neurons, each responsible for processing and transmitting information, working in unison to perform complex tasks. That's the essence of a neural network. Just as our brains learn from experience, neural networks learn from data, adjusting their internal connections to improve their performance on a given task. At the heart of a neural network lies the perceptron, the fundamental building block that mimics the behavior of a biological neuron. Each perceptron receives inputs, applies weights to them, sums them up, and passes the result through an activation function, which determines whether the neuron should fire or not. These interconnected perceptrons, organized in layers, form the backbone of a neural network, allowing it to learn complex patterns and relationships from data. The true power of neural networks lies in their ability to learn hierarchical representations of data. Unlike traditional machine learning algorithms that rely on handcrafted features, neural networks automatically learn the most relevant features from the data itself, extracting increasingly abstract and complex representations as information flows through the layers. Deep learning, a subfield of machine learning, takes the concept of neural networks to the next level, quite literally. While traditional neural networks typically consist of a few layers of neurons, deep learning models boast architectures with dozens, hundreds, or even thousands of layers, earning them the moniker deep networks. This depth of layers is not just for show, it's the key to unlocking the extraordinary capabilities of deep learning. Each layer in a deep neural network learns to extract increasingly abstract and complex features from the data, building upon the representations learned by the layers before it. Imagine training a deep neural network to recognize objects in images. The initial layers might learn to detect simple edges and corners, while subsequent layers might learn to recognize more complex shapes, such as circles and squares. As information flows deeper into the network, layers might learn to identify even more abstract features, such as eyes, noses, and mouths, ultimately leading to the recognition of entire objects, like faces or cars. This hierarchical feature learning enables deep learning models to excel at tasks that involve complex patterns and high-dimensional data, such as image recognition, natural language processing, and speech recognition. The abundance of data in the digital age, coupled with the advent of powerful computing resources, has fueled the rise of deep learning, making it possible to train increasingly complex and accurate models. Neural networks in action transforming industries. Neural networks revolutionize industries from healthcare to automotive. In healthcare, they improve disease diagnosis and treatment. In automotive, they drive the shift to self-driving cars. Their influence spans personalized recommendations, virtual assistants, and scientific discoveries. Lights, camera, recommendations, fasten your seatbelts, cinephiles. Let's build a movie recommendation system that'll make even the pickiest film buffs say, "You get me." Imagine having a personalized Netflix at your fingertips, always ready to suggest the perfect movie. We'll focus on the core concepts and techniques that make these systems tick. Our journey will take us through collaborative filtering and content-based filtering. We'll explore how each approach works and how they can be combined. By the end, you'll have a solid understanding of these techniques. Lights, camera, recommendations. Collaborative filtering taps into the wisdom of the crowd. Imagine you're at a party, and someone asks for a movie recommendation. You overhear another guest raving about a film they loved. You'd be more inclined to watch that film. That's collaborative filtering, leveraging collective wisdom for recommendations. Imagine you're browsing a bookstore, and you tell the clerk you're looking for books similar to your all-time favorite novel. The clerk, well versed in the world of literature, might ask you about the specific elements you enjoyed, the genre, the writing style, the themes, to recommend books with similar characteristics. Content-based filtering operates in a similar fashion, but instead of books, it deals with movies and their inherent attributes. In the realm of movie recommendations, content-based filtering analyzes the characteristics of movies themselves, genre, director, actors, plot keywords, and more, to create profiles for each film. It then recommends movies with similar profiles to those the target user has liked in the past. assuming that if a user enjoys movies with certain characteristics, they're likely to enjoy other movies with similar characteristics. Content-based filtering relies heavily on the availability of rich and accurate metadata about the movies. This metadata can be gathered from various sources including movie databases, online reviews, and even scripts. The more detailed the metadata, the more accurate and personalized the recommendations. Unlike collaborative filtering, content-based filtering doesn't suffer from the cold start problem, as it can make recommendations for new users or items based solely on their profiles. However, it might recommend movies that are too similar to the ones the user has already seen, limiting their exposure to new genres and experiences. In the world of movie recommendations, as in life, combining different perspectives often yields the best results. Hybrid approaches, which blend the strengths of collaborative filtering and content-based filtering, aim to create recommendation systems that are both accurate and diverse, catering to a wider range of user preferences. One common hybrid approach is to combine the outputs of collaborative filtering and content-based filtering models, either by averaging their predictions, or by using one model to generate a candidate set of recommendations, and the other model to re-rank them. This way, the system benefits from the crowd-sourced wisdom of collaborative filtering and the personalized touch of content-based filtering. Another approach is to incorporate both user and item features into a single model, such as a matrix factorization model or a deep neural network. This allows the model to learn complex interactions between user preferences and movie characteristics, leading to even more accurate and personalized recommendations. Hybrid approaches offer the flexibility to tailor the recommendation strategy based on the specific characteristics of the dataset and the desired user experience. By leveraging the strengths of different techniques, hybrid systems can overcome the limitations of individual approaches, providing users with a delightful and engaging movie discovery experience. Congratulations! You've just completed a whirlwind tour of the exciting world of AI and machine learning, covering everything from the fundamental concepts to the intricate algorithms that power this transformative technology. We've journeyed through the realms of supervised and unsupervised learning, explored the intricacies of classification and regression algorithms, and delved into the depths of neural networks and deep learning. As we've seen, AI is not some distant science fiction fantasy. It's a reality that's already shaping our world in countless ways. From the personalized recommendations we see on our favorite streaming platforms, to the self-driving cars that are poised to revolutionize transportation, AI is changing the way we live, work, and interact with the world around us. But this is just the beginning. As AI continues to advance at an unprecedented pace, we can expect to see even more groundbreaking applications emerge, transforming industries, solving complex problems, and unlocking possibilities we never thought possible. From healthcare to finance, education to entertainment, AI is poised to revolutionize every aspect of our lives. The knowledge you've gained in this crash course is not just about understanding how algorithms work, it's about grasping the immense potential of AI to solve real-world problems, improve efficiency, and enhance our lives in countless ways. It's about becoming an informed citizen in an increasingly AI-driven world, capable of engaging in meaningful conversations about the ethical implications and societal impact of this transformative technology. As we stand on the cusp of this AI revolution, it's natural to feel a mix of excitement and uncertainty. The rapid pace of advancement can be overwhelming, and the sheer breadth of AI applications can make it challenging to know where to begin. But remember, the journey of 1,000 miles begins with a single step. The key is to embrace a growth mindset, to approach AI with curiosity and a willingness to learn and adapt. Don't be afraid to dive in, experiment, and make mistakes. The beauty of AI is that it's a constantly evolving field with new discoveries and breakthroughs happening all the time. Embrace this dynamic nature and view it as an opportunity for continuous learning and growth. Whether you're a student, a professional, or simply someone who's curious about the future, there are countless resources available to help you deepen your understanding of AI and machine learning. Online courses, books, tutorials, and communities offer a wealth of knowledge and support, making it easier than ever to embark on your AI journey. So, what are you waiting for? Embrace the future, one algorithm at a time. Explore the vast possibilities of AI and discover how you can be a part of this transformative journey. The future is unwritten, and it's up to us to shape it with the power of AI. Don't forget to like, comment, share, and subscribe. Use the promo code in the description section to enroll in our AI and machine learning masterclass at a 50% discount. Explore our video library and check our video on computer vision. Thanks for watching.